a thermodynamic system can do work. Now, the easiest way to think about that is to think about a gas. Right? So let's say initially I have a cylinder or something like that, which has, say, a piston on the inside. So here's my piston, which is, say, floating on some gas. So here are all my gas particles on the inside. So these things moving around, we know that they have a kinetic energy. We know by the kinetic theory that as long as they have a kinetic energy, they also manifest themselves as pressure. So this is going to have some sort of pressure. Okay? So now let's say I put a fire under this situation. So that initially this thing was at some initial location. Call that y is equal to 0. And then I'm going to add my fire. So here's my fire. I'll put a Bunsen burner or something like that under here. So that Bunsen burner then is going to cause some heat transfer into here. So let's say initially this thing is at some initial position, y is equal to 0. So as the energy then increases, that then means that the pressure then is going to increase, which means that ultimately that's going to apply itself as a force and going to cause this piston to lift upward. So at some later time, what will happen then is that the piston now is going to move up to this location. So again, here's my gas, which has an increased kinetic energy because the temperature has increased. So now it's at this location, so it has moved up by an amount of, let's say, y, because the gas has changed its force and now has applied a force in this direction. So this is going to be F gas. So let's think about how much work the gas did. So this is going to be the work done by the gas. Now, remember when it comes to work, we talked about this before. When we talk about work, we have to talk about perspective. In this case, I'm talking about the work done by the gas. If I was going to do the work done on the gas, I would just need a negative sign here. But we'll talk about that eventually. Good. So the work done by the gas is what we know work is. So here, let's assume that for now, that the force of the gas is simply equal to a constant. So I'm applying a constant force. So we know this is then going to be the same thing as the force, which in this case is the force by the gas, times the distance at which it moved, which is then y, times cosine of the angle between the two. But in this case, since the force is upward, the displacement is also upward, I get a cosine of 0, which is simply equal to 1. Okay. Good. Now, what we know, though, is that this was the result of an increased pressure. So we can also write this in terms of the pressure, using the fact that, again, the force is the same thing as the pressure times the area. So this is going to be the pressure times then the area times then y. So what is this? Well, initially, this thing had some area here. Right? So this is the cross-sectional area A. This is the cross-sectional area A, which means that initially this had some volume. So now what has happened then is I have increased the volume, delta V, by an amount of A times Y. So ultimately what happened then was what? The work done by the gas has caused the pressure to then change the volume. Right? So this is how we're going to define then work. So the work done then by a gas is then simply going to be equal to the pressure times then the change in volume. So again, here, this is applying a force upward, which means ultimately has changed this amount of volume here. So again, it has changed this height. This has a cross-sectional area. Let's simply call that A. So ultimately then, the work that is being done then is simply equal to the pressure times the change in volume. Now, this is true, again, if the work was equal to a constant, which means the pressure is equal to a constant as well. So here, this has to be true when pressure is equal to a constant. But in a lot of situations, the pressure can actually be volume dependent. For example, an ideal gas. Right? So an ideal gas, in that case, the pressure depends on the volume. So if that's true, so if the pressure is actually a function of the volume, in this case, what we have to do then is we have to consider small changes as this thing has being moved, such that the pressure is constant approximately across that change in volume, which means we're going to chop this thing up into a whole bunch of small different sections, where each one of these is going to have a differential change in volume. Then to find the total work, we then have to sum over all the works which are done by increasing it by some differential amount of volume. which means we're going to do an integral. So in the case where the pressure is actually a function of the volume, work then is simply equal to the integral of the pressure integrated over the volume. So this is then going to be the work. So the definition of then the work done by the gas is equal to the integral of the pressure integrated over the volume. But if the pressure is equal to a constant, this thing reduces down to this, right? Because in that case, I can pull the pressure out of the integral. So I get pressure times the integral of dV, which is simply equal to the change in V. So this is the work done. Now, the way we usually think about work, and the way we can usually interpret work, the easiest way to think about it is in terms of what's known as a PV diagram. So let's introduce the idea of a PV diagram. So a PV diagram is a pressure versus volume. So here, this is volume across this axis. This is pressure. This has to be in pascals, and this has to be in meters cubed. So PV diagram is the best way to think about work because, for example, if I start off at this point, where this is my initial pressure with my initial volume, and then I increase to this pressure, so this is going to be my final pressure, and this will be, say, my final volume, so that I'm going to look at, say, this point, and let's say I increase, so I'm going across this line here. Well, why we want to use these PV diagrams is because the pressure versus volume gives me the work, which means the work then is simply the area underneath this curve. So anything under here is equal to the work. So if we think about looking at PV diagrams, the work then is simply the area under the curve on this PV diagram once I know the initial and final pressures and the initial and final volume. Now, things to talk about. This again is the work done by the gas. If I wanted the work done on the gas, I would just have to take a negative sign from there. Now, other benefits of using PV diagrams, which we'll talk about as we actually get there, but it tells me a whole bunch more than just simply the work done. Because even though it does tell me the work, which is simply the area under the curve, it's also going to tell me a lot about things like initial temperatures, final temperatures, pretty much anything that is of interest in a thermodynamic system is included inside of the PV diagram. So let's do an example and let's see how this is actually done. Now, as we can see, since this thing is going to depend on the area under the curve, the amount of work that's going to be done is going to be dependent on how I go from one point to another point. So let's say that I'm going to initially start off with my gas. So this is in, again, volume meter cube. This is in pressure pascals. And we're going to start off at some initial point. So let's say this is at 1 meter cubed at 1 Pascal. And then I'm going to increase this to 3 pascals and 3 meters cubed. So I'm going to start off at this point and I'm going to end at this point. And I'm going to go directly across this line here. Okay. So this is going to be, I'm going to expand my gas, for example. So I'm going to expand it, it's causing my system to expand. Then I'm going to compress my gas, and I'm going to do that such that we're going to go straight down here to 2 pascals, so along this direction. And I'm going to hold it at 2 pascals, but then compress the volume to then 2 meters cubed. And then I'm going to decrease the pressure again to 1 Pascal, and then compress my gas along this direction from 2 meters cubed to 3 meters cubed. So good. So we want to see is along process 1, where I'm actually expanding. So where's my blue go? We want to know how much work was done here. So we want to know what was work 1 equal to. And then while I'm compressing this, let's call that path 2, we'll want to know how much work was done there. And again, we're going to take the viewpoint that we want to know what is the work done by the gas, not the work done on the gas. And then if we wanted to know the net work going from this point, let's call that point A, through to point B and then all the way back to point A, we can then simply add those two works together. Because again, this one is going to have a positive work, this one's going to have a negative work because it's actually being compressed. Good. Now, these lines here, these are what are known as isovolumetric. Volumetric, which means that what? We are changing the pressure while holding the volume constant. That's what this thing means. Now, in this case, since there is no change in volume going from here to here or here to here, there's going to be zero work which is done along this path and along this path. So, let's talk about one first. So first off, we can easily split this thing up into then two areas, since I want to know the area under the curve anyways. So I'm going to look at the area then of the triangle, plus then the area of the rectangle, right? So this is now going to be, so work one is going to be the area of the triangle, since it's the area of the curve, plus then the area of the rectangle. So for the triangle, we know this is going to be equal to 1/2 the base. Our base in this case is simply going to be, what, 3 minus 1, which is 2, so that's 2 meters cubed, times then the height, which is then simply going to be also 2, and this is going to have units of pascals, plus that of the rectangle, so it's going to be the base, which is also going to be 2 meters cubed, times the height, which is simply going to be 1 pascal. So multiply this through, what I find in this case then is that this is equal to 4 times 10 to the 5th joules, because that's a work. Right? Now, along path 2, again, going from here to here, that's going to be 0 work. Going from here to here is also going to be 0 to work. So again, I can simply cut this up into two rectangles. So I'm going to look at here, area of the left rectangle, call that L, and then here, area of the right. That doesn't work. Let's call that capital R. We call that capital L. There we go. So it's going to be simply equal to area of the left plus area of the right. Now here, my volume is decreasing, so these are both going to be negative. So it's going to be equal to negative of the base, which is simply going to be 1 meter cubed, right, times the height, which is then, what? So this is at 2 to 2 pascals, minus then also 1 meter cubed times 1 pascal, which is then going to be minus 3 times 10 to the 5th pascals. So you're probably wondering where that 10 to the 5th is, because this is actually 10 to the 5th. So this is in units of 1 times 10 to the 5th pascal. So great. So these are a couple examples of calculating the work. So again, when we think of the work, it's easiest to think about these PD diagrams. So in this case, we simply know that the work is simply equal to the area under the curve of these PD diagrams. Now, once we start talking about thermal processes and we start talking about the first law, we'll eventually point out how this actually tells us more information, things like what's the initial temperature and etc. But for now, we know that these things actually then give us the work as well.